Welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research, from advanced biomedical technologies to breakthroughs in AI, material science, chemistry, and physics, all told as compelling, easy-to-follow stories. And, today we are getting into something that, well, if you're like most people, when you think of nuclear waste, your brain probably goes straight to pop culture.
Oh, yeah, absolutely.
Right, like I'm thinking of The Simpsons, Homer Simpson at the power plant tossing out this glowing green rod of radioactive goo,
Yeah.
and it immediately mutates a fish into having 3 eyes.
Right. Classic.
We had this ingrained image of nuclear waste as this highly visible neon green monster that's, super obvious and easy to spot. But in reality, the true nature of radioactive waste isn't a glowing green blob at all. It's an incredibly stubborn, totally invisible chemical puzzle.
It really is. I mean, it's a very pervasive Hollywood image, but you're spot on. The reality of nuclear waste is far less theatrical, but chemically. Chemically, it is infinitely more complex.
Yeah.
We're dealing with a microscopic problem that has massive, global consequences for how we generate power and manage its aftermath.
Which brings us to a really strange question for you to think about today. Why is it so impossibly hard to separate one specific type of radioactive metal from another? And how could a single, highly unstable, quote-unquote, radical molecule be the key to solving a decades-old nuclear mystery?
It sounds a bit like an impossible riddle, honestly.
It really does.
But it represents a very real, very physical challenge that chemists have been banging their heads against for half a century. And to understand the solution, we really have to understand the magnitude of the problem itself.
Okay, so let's look at that core problem of nuclear waste separation. When we produce commercial nuclear power, the reaction generates electricity, obviously, but it also leaves behind these highly radioactive waste byproducts.
Right.
And one of the absolute most problematic elements in this whole waste stream is americium.
Exactly, Americium, which is named after the Americas, by the way.
Oh, really? I didn't know that.
Yeah, and it is incredibly radioactive and generates a tremendous amount of heat. So to deal with commercial nuclear waste safely, whether your goal is to recycle the viable material or just store the dangerous byproducts long term, we absolutely must separate the americium from the other elements in the waste stream.
Right, you can't just leave it in there.
No, you can't. And the main issue is that americium doesn't sit in isolation. It gets intimately mixed up with a group of elements called lanthanides.
Wait, okay, so if we know americium is the highly radioactive problem child, right? And we know it's mixed with these lanthanides, what actually happens when we try to run a standard chemical extraction on this waste? Why can't we just filter it out? Is it like trying to separate salt from sugar while blindfolded?
Oh man, it's even harder than that.
Really?
Yeah, it's like trying to separate identical twins in the dark where the only physical difference is that one twin has slightly longer fingers.
Oh, wow. Okay.
Yeah. For decades, scientists have been intensely frustrated because americium and the lanthanides, specifically elements like neodymium and samarium, they behave like chemical identical twins.
Because they share the standard electrical charge, right? Which is +3 for both.
Right, exactly.
And their atomic radii are virtually indistinguishable. So standard chemical extractors they just grab both indiscriminately, right?
That is the crux of the issue. They are what we call near isoradial. So if you introduce a standard chelating agent, or like a chemical net, to grab the americium and pull it out of that highly radioactive soup,
The net just catches everything.
precisely, the chemical forces involved will just as happily grab the neodymium or the samarium. So you haven't actually separated the dangerous material from the less dangerous material. You've just moved the entire mixture from one place to another.
Okay, wait, so let's talk about those longer fingers you mentioned. That's a great analogy. So because americium's 5-Aus and 6-P electron orbitals aren't quite as radially contracted as earlier actinides like uranium, for example, they have just enough spatial extension to actually engage in covalent bonding.
Yes.
And that's something the identical lanthanide twins simply can't do, right? With their tightly pulled in 4Fa orbitals.
You're touching on the real bottleneck right there. That subtle spatial extension, that is the longer fingers of our identical twin. But the problem is that difference is practically invisible.
How invisible are we talking?
We are talking about americium's 5 orbitals extending just a microscopic fraction of an angstrom further out than the lanthanide's orbitals.
Jeez.
Yeah, so building a chemical system sensitive enough to recognize and exploit that minuscule extension and actively share electrons in a covalent bond with americium while completely ignoring the lanthanides, it's been a monumental hurdle.
So how did scientists figure this out? Like, if the difference is practically invisible, how do you build a chemical magnifying glass to see it?
Yeah.
And, this is where the story gets really interesting. Because if traditional chemical nets can't tell these twins apart, chemists had to stop looking at the whole atom and start looking for a way to exploit that fraction of an angstrom difference.
Exactly.
And that's what drove the team at Los Alamos National Laboratory to try something, well, borderline reckless, didn't it?
It definitely required pushing the absolute limits of synthetic chemistry, I'll say that. So in a study published in the Journal of the American Chemical Society in March 2026,
Okay.
researchers Daniel J. Lessier, Maria J. Beltran-Leyva, Enrique Arbatista, Andrew J. Gaunt, Ping Yang, and their team at Los Alamos discovered something completely unprecedented.
Los Alamos. I mean, the birthplace of the atomic bomb. It makes total sense that they are the ones still pushing the boundaries of what's possible in actinide chemistry.
They really have the facilities for it, which is crucial because this was a remarkably high-stakes, delicate experiment. The team was working with Americium, but a very specific isotope. They used Americium-243.
No, wait. Most people might only know Americium-241, if they know it at all, because it's used in tiny, tiny amounts in household smoke detectors.
Right.
But Am-241 has a half-life of like 433 years, meaning it emits a massive amount of intense radiation very quickly.
Right.
But Am-243 has a half-life of 7,370 years.
So did they go with the heavier isotope just to buy themselves a slight margin of safety for the chemistry?
That's the rationale, yeah. Because Am-243 decays much more slowly. It is slightly less radiotoxic to handle on a second-by-second basis compared to 241.
Okay, that makes sense.
But we have to be clear here. Safer is a highly relative term.
Yeah, I'd imagine.
It is still a highly radioactive alpha emitter.
Yeah.
And to do this chemistry, they were working with an incredibly small amount of material, just 5.8 milligrams.
Wow. We are talking about a radioactive sample roughly the weight of a grain of sand.
Exactly. How do you even begin to manipulate 5.8 milligrams of an alpha inner inside a, specialized moisture-free protective glove box?
Cool.
Let alone try to isolate a chemical difference measured in fractions of an angstrom.
It requires an unbelievable level of technical mastery. I mean, the scientists decided their best bet was to utilize a specially engineered molecule called a redox active ligand.
Go.
Specifically, it was a complex bipyridine derivative. We don't need to get bogged down in the exact IUPAC name, but...
Yeah, let's keep it simple.
Right. But the genius wasn't just in the structure of the ligand, it was in the state they pushed it into. They chemically manipulated this ligand into a radical state.
Ah, the radical molecule. Okay, and just to ensure we are all visualizing this the same way, when we talk about a radical state here, we are looking at a molecule that possesses an unpaired electron, right?
Yes, exactly.
Since electrons strongly prefer to exist in pairs to maintain stability, this radical ligand has a single, highly reactive electron essentially scanning its environment, desperately searching for a partner to share spatial overlap with.
That is a brilliant way to picture it. The researchers took this highly reactive radical ligand with its lonely searching electron.
They're looking for a home.
Yeah, looking for a match, and they introduced it to that tiny 5.8 milligram speck of Americium-243 inside the controlled environment of the glove box. And the hypothesis was that the radical's unpaired electron would be aggressive enough to find and lock onto those longer fingers, the slightly more extended 5-4 orbitals of the Americium.
And this led to the massive wow moment of the research paper. Because they actually achieved the synthesis.
They did. They really did. The team successfully synthesized and grew these dark orange crystals of a brand new molecule, which they designated as 1AM.
1AM.
It represents the first ever isolated, structurally verified americium complex that contains a radical ligand. Prior to this, nobody had ever managed to successfully trap an americium atom in a covalent handshake using one of these radical molecules.
That's incredible.
Yeah.
But, growing a few tiny dark orange radioactive crystals is really only the first half of the battle. You can't just look at a crystal and confirm covalent bonding. So how did they physically prove that the lonely electron from the radical ligand actually reached out and engaged with the americium's 5 orbital?
Well, to physically map that interaction, they relied heavily on X-ray diffraction.
Yeah.
By firing X-rays through the crystal lattice and measuring the precise angles and intensities of how those rays scatter, they can calculate the exact 3-dimensional spatial coordinates of every single atom in the molecule.
Like a blueprint.
Exactly like a blueprint. And then they paired this physical data with incredibly intensive supercomputer simulations using density functional theory, or DFT.
To mathematically model the quantum mechanics of the electron behavior, right?
Spot on.
Okay, and this is where the identical twin aspect comes back in. Because the paper notes, they ran the exact same experimental synthesis using neodymium as a control.
Yes.
So they run the identical twins through the exact same X-ray and DFT process. What do the structural blueprints actually show when you put the americium complex side by side with the neodymium complex?
The blueprints revealed a definitive chemical signature. The physical bonds between the americium atom and the nitrogen atoms of the radical ligand were noticeably shorter than the corresponding neodymium-nitrogen bonds.
Oh, wow. How much shorter are we talking?
Up to 0.037 angstrom shorter.
Wait, 0.037? Because an angstrom is 1/10,000,000th of a meter. To the human eye, that sounds like a rounding error. But at the atomic scale, when you're analyzing bond lengths, a contraction of 0.037 angstroms is a massive structural shift, isn't it?
It is monumental in this context. It is the physical proof of covalent bonding. And what's fascinating is how that actually plays out physically, as confirmed by the density functional theory computation.
Right.
The shortened bond proved that the lonely electron from the radical ligand didn't just sit next to the americium. It actually reached in and overlapped with the americium's elusive 5s orbital.
It successfully grabbed those longer fingers.
Exactly. It formed a highly specialized bond known as a pi interaction. The supercomputer calculations show that this specific atomic handshake contained roughly 10% americium-5 character.
Okay, so that means 10% of the atomic orbital making up that bond was pure americium actively sharing its electron space.
Yes.
And when they looked at the neodymium twin,
Complete failure to engage.
really?
Yeah. The neodymium was utterly incapable of forming that pi interaction. It just sat there, bound ionically to the ligand through basic electrostatic attraction, like static cling, basically, but it couldn't extend its 4f orbitals enough to actually share the electron.
Wow. Okay, so zooming out from the subatomic scale, what does this actually mean for you, the listener? Why does a 0.037 angstrom difference matter outside a high-tech glove box in New Mexico?
Right.
Because by using this radical ligand, the team at Los Alamos proved, beyond a shadow of a doubt, that americium can form unique covalent bonds that its lanthanide twins simply cannot. They finally built the chemical magnifying glass that can tell the twins apart.
And the implications of that are staggering for the energy sector. I mean, this isn't just an abstract triumph of quantum chemistry. This is foundational data that could revolutionize how we approach the entire back end of the commercial nuclear fuel cycle.
Because the entire bottleneck in efficiently treating and recycling nuclear waste has been the lack of a reliable mechanism to strip the highly radioactive americium away from the bulk lanthanides.
Precisely. If chemists understand the precise quantum mechanics of how americium engages in covalent bonding, how much 5 characters involved, what specific ligand architectures favor that overlap, they can design highly efficient industrial-scale separation extraction processes.
You mean you could theoretically engineer a chemical filtration system that exploits that specific pi interaction, acting like a highly targeted sponge that only absorbs the americium out of the waste stream while letting the lanthanides wash right through?
That is the ultimate goal. And achieving that leads to vastly cleaner, safer, and much more manageable nuclear energy.
Because you isolate the worst stuff.
Exactly. If you can efficiently pull the dangerous heat-generating americium out of the waste, the volume of high-level waste that requires long-term geological storage drops dramatically. The radiotoxicity burden of what remains is significantly reduced. It fundamentally changes the math on nuclear power's environmental footprint.
That alone is massive for the future of global clean energy. But the paper doesn't just stop at waste separation.
No, it doesn't.
The researchers also ran cyclic voltammetry on these newly grown crystals. What exactly were they looking for by zapping this complex with electrical currents?
Well, cyclic voltammetry allows chemists to see how a molecule handles the addition or removal of electrons under an applied voltage. So they're looking for stability and reactivity. And what they found was that this new 1am complex exhibited reversible redox features.
Okay.
In the context of the paper, they suggest this indicates the molecule could potentially act as an am to synthon.
Let's translate that for a moment. So in synthetic chemistry, a synthon is essentially a structural unit within a molecule that acts as a reliable starting point, or a springboard for further, more complex chemical reactions, like a chemical building block, right?
That's a great way to frame it. To take that a step further, consider a field called small molecule activation. There are certain incredibly tough chemical bonds in nature, like the triple bond holding nitrogen gas together, or the strong bonds in carbon monoxide.
Right, super stubborn bonds.
Exactly. And breaking those bonds to use the constituent atoms for building pharmaceuticals or advanced materials usually requires highly reactive transition metals acting as chemical sledgehammers.
But americium isn't known for being a chemical sledgehammer. In its standard state, it just stubbornly sits at that +3 oxidation state. It doesn't want to dynamically give or take electrons to facilitate other reactions.
Historically, yes, americium has been considered quite chemically boring in that regard.
Uncooperative.
Highly uncooperative. But the cyclic voltammetry data suggests that by attaching this specific radical ligand, they might be able to act like a battery pack, temporarily coaxing the americium down into a highly reactive +2 oxidation state, the Am2 synthon.
Which means this complex could serve as the catalyst to kickstart chemical reactions that were previously thought utterly impossible for americium to participate in.
It cracks open an entirely new frontier in actinide chemistry. I mean, we're moving from simply trying to contain americium to potentially using its unique heavy element properties to break tough molecular bonds and synthesize entirely new classes of materials.
It is genuinely wild to trace the arc of this story. We start with the pop culture myth of glowing green goo, and we arrive at the reality. A team of scientists manipulating a few radioactive grains of sand inside a glove box, using a single lonely electron to force an unprecedented subatomic handshake.
It highlights a really beautiful, almost poetic irony in modern science. We are faced with this massive, macro-scale global industrial problem. What to do with tons of highly dangerous commercial nuclear waste. And it turns out the key to solving that macro problem requires understanding the delicate quantum-level sharing of a single electron at the absolute limits of human observation.
Wow.
The solution wasn't found in a massive industrial machine. It was hiding in a space measuring a fraction of an angstrom.
It really puts the scale of scientific discovery into perspective. They didn't just solve a 50-year-old puzzle about atomic twins. They unlocked a door that could change the future of energy and chemical synthesis. And it leaves you wondering, if this discovery is just the baseline, if we can now predictably manipulate the bonding of highly radioactive heavy elements at will and coax them into these unprecedented molecular handshakes, what kinds of impossible chemical reactions might scientists uncover next? Thank you so much for joining us in the Deep Dive Lab today. If you enjoyed uncovering this mystery with us, please make sure to follow and subscribe for more fascinating science stories unfolding in real time. Until next time, stay curious.